Welcome back, Physics 30. This is the beginning of this conservation part 1 unit, CO1.1, work done by a constant force. So the objectives here will be distinguishing between work in the scientific sense as compared to the everyday sense, write the definition of work in terms of force and displacement, and calculate the work done by a constant force when the force and displacement vectors are at an angle. And lastly, distinguish between positive, negative, and no work being done in the physics sense. So the word work has a variety of meanings of everyday language, but in physics, work is specific to describe when we have a force acting through a distance. So you have to have someone applying a force or something applying a force, and that object actually has to move. Then the work done on an object by a constant force, constant both magnitude and direction, how it's calculated is the product of the force multiplied by the displacement. And we're looking at the force that is in the same direction, along the same axes as the displacement. So that's where this comes into play. So F parallel, those two lines there indicate F parallel. So the force that's parallel to the displacement. So that's what's illustrated right here. F parallel is the component, so the vector component, that is parallel to the displacement. So if you look at this picture on the bottom of the page here, this person pushing a box to the right. So the box is moving to the right, so it's undergoing a displacement here. And if we're looking at the force that's in the same axis as that, that would give us the work done. So force, of course, is Newton. Displacement is meters. So it's Newton meters, which also is signified by a big J for joules. If we look at the next page, continue on. So if we look at an example here, an applied force of 20 newtons was used to push a box 8 meters along the floor. How much work was done? So it's really easy. So the force that we applied was 20 newtons. The displacement is, and both these are vectors, 8.0 meters along. And so W equals F parallel multiplied by D. So often we just simply write it like that. So 20 multiplied by 8.0. So Newton meters, that's 160 Newton meters. Put a line over top of that because 3 sig figs and 3 sig figs. Or of course, 160 joules. All right, so it's that easy, ladies and gentlemen. Just simply force multiplied by displacement, the amount that it actually moves. So look at another example here. How much work is done in lifting a 5 kg pail of vertical distance? Here we'll assume constant velocity. And we know what happens when we have something moving at constant velocity. So if we're lifting something up, let's call it the F parallel. And this object is going to move in this direction. So of course what we're counterbalancing here is Fg. So if I can figure out what Fg is, I'll be able to figure out what F parallel is, etc. So Fg is equal to mass times gravity. So it is a 5 kg pail multiplied by negative 9.8. That's going to give us negative 49.0 newtons. And of course, if I analyze this situation vertically, the net force vertically is equal to my parallel force summed with the gravity force. And of course, since I said this, that means that F net is going to be 0. So we rationalize it that way. So add 49 to each side, add 49, and of course, yes, F parallel must be 49 in order to lift that object straight up. So W equals force multiplied by D. So exerting 49 newtons, a distance of 1.5 meters. So it works out to be 73.5 joules. Okay, so not bad. So horizontally, F and D are in the same axis. Here, D and F parallel, you can see, are both moving upwards. So that's the component that we use. Now, if we are pulling something at an angle, of course, we have to find that component. So, for example, if we look down below here, if this person here is pulling the box to the right, so D is parallel to the right, but we're pulling up at an angle. And yes, we can think of this again as being made up of a horizontal component and a vertical component. So you have really Fx and Fy. And of course, we're concerned about Fx. That is the one that's going to pull us in the right direction. So if I look at the bottom here, let's just kind of redraw that here. So I have my force being pulled like this, have my Fy, and Fx really is F parallel, right? It's the force that's parallel to the movement here. And of course we have angle here. So if we take a look at the trig function, we're given this, we're looking for that. So of course adjacent over hypotenuse, that's cos of theta. And solving for F parallel, it's just F cos theta. So over here, when I had my original equation, F parallel D, to find F parallel, it's either the force I'm pulling at an angle multiplied by cos of theta. And notice that's what we have right there. So no matter what the force I have, I can use this. Now, if I'm pulling at it to the right, my angle, my force angle, of course, is going to be 0. And those of you from pre-calc theory remember that the cos of 0 is actually 1. So this would work out to be 1 and it wouldn't change. Otherwise, I'd have to figure out that component. So this equation works all the time, even when I'm not pulling at an angle, because the cos of 0 is 1. So F is the magnitude of the constant force, D is the magnitude of the displacement, and the angle there is the angle between the force and the horizontal movement of the object. Okay, we'll look at the example on the 3rd page. So we'll kind of look at pulling at an angle, maybe something else. A person pulls a 50 kg crate along a 40 meter surface, as you see here, by a constant force of 100 newtons. So that's this pull right here. This is going to be 100. That angle force is 100. The floor has friction working 50 newtons against you. So there we have that friction force. Determine the net work being done. So if we're determining the net work, this is a little bit different. Net work, we're going to be using the net force. So not just F parallel. We're going to have to consider the friction here to see overall net what is going to be happening here. So it's slightly different here, ladies and gentlemen. So if we look at what's going on horizontally, okay, so we have our angled force. Of course, we need to figure out F parallel here. So we need to figure out F parallel, that force that's pulling to the right. Now, of course, to do that, we're going to have to figure out what F parallel is. Okay, so F parallel is equal to 100 multiplied by cos 37 degrees. F parallel equals 79.9 newtons. So if we look at the scenario horizontally, okay, all my horizontal forces consist of my F parallel pulling to the right, and we have friction working against us like that. So the F parallel, let's see, it's 79.9, I believe. So it's plus 79.9, and my friction is negative 50. So, oh yes, that's going to give a net force in a particular direction of 29.9. And I'll put a pause in front of there indicating it's going to the right. So overall, even though you're pulling with enough force to have 79 29.9 working to the right. 50 is going to subtract some off so that you end up with overall net work of being 29.9 newtons. So if I look at this, let's call this, so this is net work. So it's going to be using net force. So that 29.9 newtons multiplied by my 40 meter distance, it's going to give 1,196 joules. And I think we run it off to 3 sig figs. It's going to bump up to there. It's going to give 1,200 joules, with this digit being significant. Okay, what we'll do is we'll stop there. Part 2, we'll look at hopefully the rest of it and then go on from there.